There we go. Okay, so for this one, the first thing I would do is look at what does this mean? Okay,
Mic off. Mic on.
so on one end we have that on the lower end we have that 0 is equal to x minus 3y. And then on the other end, we have 2 equals x minus 3y. Right, so I can solve this, and I have y equals 1/3 x, and I have y equals, what was that, 2 minus x all over 3. And then I do the same for the other one. Right, I have 0 equals x plus 3y, which gives me y equals minus 1/3 x, and oh yeah, and 2 equals x plus 3y, which is the line um, y equals 2 minus x all over, this should be negative positive, because I divide by -3. Anyways, I get this all over 3. Okay, so if I graph this, right, these are the curves I'm graphing. 1/3 x, it's going to look like this. Uh, negative 1/3 x, it's going to look like this. And then 2, uh, let's see, 2 minus x over, let's see, minus 2x plus x over 3. That's, so minus 2 somewhere down here. That's going to look like this. It's got the same slope. It should have the same slope. Should be parallel. Still on the same slope, whatever. And then 2 minus x, that's going to be parallel to this, passing through the point minus 2. Okay, so we want the region that's where this, basically it's below this line, below the line x minus 3y equals 2. Right, so that's below, well, actually, let me not say below, but let's just say that we want the region that is enclosed by all of these, right? So this is the region we're interested in. Okay, so let me just label these. This was the line y equals 1/3 x. This was the line y equals negative 1/3 x. This one was the 2 minus x over 3. And finally, we have this one, which was minus 2 plus x over 3. Okay, so there's two ways I could do this. The first way is the straightforward way. That's the way I imagine most everyone did this. But I'm going to show another solution to this also. So here, right, we're going to integrate, vertical strips. But it's going to change. So here I'm going from, let's see, so I'm integrating the bottom curve. So I'm going from negative 1/3 x all the way up to this other curve, 1/3 x. And this is the function I'm integrating, 9y squared. Integrating that with respect to y first. And then we want to integrate that from here all the way up to, well, notice we're going to have to stop. Okay, that's kind of, it's not straight. It's supposed to be lined up. It's supposed to be square. Basically, we're going to have to stop where it switches from one curve to the other curve. Right, so we're going to have to go from 0 up to, I need to figure out what that point is. I'll come back to that. I'll come back to that. But then from here, going on to where till they intersect, that's going to be, so from wherever to wherever they intersect, I'll fill those in a second. Now I'm integrating from this bottom curve minus 2x plus, oops, minus 2 plus x over 3 all the way up to 2 minus x over 3. Same curve. Minus 9y squared dy dx. Okay, so I need to figure out where do they intersect. So let's just solve this one right here. So I have minus 2x over 3 equals minus 1 over 3x minus 2 plus. Okay, so the 3's cancel, multiply both sides by -1, and I have minus 2 plus x equals, oh sorry, equals -x. So we solve and we get x equals 1. So this is the point x equals 1. So that's where I'm going to stop this integration, put a 1, and then that's where this one starts. And then I need to figure out what is this point. So I'm going to look at when do these two curves intersect. So I'm going to see when does minus 2x over 3 equal minus 2 plus x over 3. Okay, so we cancel the 3's on both sides. And then we move this x over to that side, move this 2 over this side. We have 4 equals 2x, so x equals 2. So right here, this is x equals 2, which is where I'm going to stop integrating. So we're integrating from 1 to 2. And that's my integral. Okay, so that's that's going to work. That's fine. But it's also a lot of, it's going to be a lot of integrating, and it doesn't look fun. So I'm going to show you guys another way to do this. That's a little bit, the integral that you get at the end is a little bit simpler. So we have to do some work first, and then the integral we get at the end will be a lot simpler to integrate. So if we look at the graph, right, it looks something like this. No, I need, I can't draw the shape, can I? Nope. Okay, so it's supposed to be like all the sides are the same length. Okay, so think of this as supposed to be like a kind of a rotated square. So one thing I could do if I wanted to make this a really simple integral is I could, one, rotate it, and that would be enough, but so I could rotate, not integral. So if I rotate it, what's it going to look like? It's going to look something like this. Okay. But then these bounds might not be in very easy to find places. So I'm going to go ahead and also shift it like this. Okay. So, and when I do that, um, this should be fairly easy to integrate. Okay, so how can I do that? Well, I know how to do, well, actually, so the transformation that we want is actually going the other way. Um, it's the one that goes this way. No, sorry. Yeah. Okay, so how do I rotate it? So this is just a fact that I happen to know. So I don't expect you guys would have done this unless you just happen to know this transformation also. But if I want to rotate an object, I can use the transformation. All right, so I'm doing this one first. X equals sine theta, nope, cosine theta, u plus sine theta v, and y equals minus sine theta u plus cosine theta v. And what this is going to do, it's going to rotate some object um, by 45 degrees. Okay, so it's going to rotate it by theta. So if I plug in 45 degrees or pi over 4, what I get is the transformation x equals 1 over root 2u plus 1 over root 2v, y equals negative 1 over root 2u plus 1 over root 2v. Okay, so that's this one. So I rotated it, and now I want to shift it over. I want to shift the x coordinates over by 1. I don't want to change the y coordinates, but I want to shift the x coordinates by 1. So I'm just going to add 1. Actually, is it 1 that I want to add? I don't know that it's 1 that I want to add. What is the... You know, I'm not going to worry about this one. Sorry, I messed that up. I'll just say we'll rotate it so that it's a square. Maybe we can rotate it later if we want. So if I do this transformation, what do the bounds become? So if I have 0 less than or equal to, what was it again? X minus 3y. And I plug this in, then what do we get? I have 0 less than or equal to 1 over root 2u plus 1 over root 2v minus 3 times y, which is minus 1 over root 2u plus 1 over root 2v. Let's see. Section example 1 is similar to this problem. Let's see, what did they do in the book? Hold on, let me pull that up. Okay, so Ethan says in the book, section 15.9, example 1 is similar. Okay, so let's see what they... Yeah, okay, so that's what was the transformation they did? Example 1. Oh, I see. Okay. Okay. Yeah, you know what? That's going to be easier than using something you guys don't know. So let's do it this way. Okay. And I may need to restart this program. Okay, so what we want actually, instead of this, we want a nice regular region. So maybe we could do something like this, where we have a nice 1 by 1 rectangle. So we want to get from here to here. Uh, right, so this is the line x minus 3y equals 2. This is the line x plus 3y equals 2. This is the line we said, oh, no, I'm sorry, I got that backwards. That's this one. This one is the line x plus, let's see, it's going to be x minus 3y. Wait, we get, yeah, that's x plus 3y equals 0. And this is 0 equals x minus 3y. Okay, so if we happen to just pick this for v and this for u, okay, so we have u equals x minus 3y and v equals x plus 3y. Then what does this region become? Right, this is the line, this line right here is the line, if I just redraw it, right, this line becomes v equals 2. So this is x and this is y. This is the line u equals 2. This is the line u equals 0. This is the line v equals 0. So if we actually drew this on u and v coordinates, then what we have is basically a square like this. Right, so where this is 2, this is 2. Right, so this line right here, let me pick a different color. Okay, so this line right here, the line v equals 2, that becomes this line right here, v equals 2. And then different color, let's do blue. Right, so then this line right here becomes this one. And then this is the line u equals 2 right here. And this is u equals 0. Okay, so we have kind of what our transformation is. But now we need to put this in terms of u and v, so x equals something in terms of u and v, not not the other way around. So I need to solve for x and then solve for y. So let's go ahead and add both of them together. So I have u plus v is 2x, right? The three y's cancel out. And then so x equals u plus v over 2. Okay. And then I need to solve for y. So if I subtract them, I have v minus u is going to be 6y. Yeah. So y equals v minus u over 6. Okay, so that's my transformation that I want to use. Okay, so now to do the integral, let me do the Jacobian. So remember that's dx du, dx dv, dy du, dy dv. And what I get is, that's going to be 1/2, 1/2, 1 minus 1/6, and 1/6. So the determinant of this is going to be, let's see, that's 1/12 minus 1/12. So that's 2/12, 1/6. Okay, and now I can actually write my integral. Okay, so I have the integral. Let's go from u equals 0 to 2, and from v equals 0 to 2. I need to write, where's my function? X squared minus 9y. Actually, let me do that first before I do this. So x squared minus 9y in terms of u and v. X squared minus 9y squared. 9y squared. That's equal to, x is this, so I have 1 over 4 u squared plus 2 uv plus v squared minus 9 over 36, yep, times v squared minus 2 uv plus u squared. Okay, and then so that cancels out to be 1/4, so I have so that's 1/4. So we have, let's see, so the 1/4 u minus 1/4 u squared, so those are going to cancel out. And then I have 2 uv plus 2 uv, so I have 2 of those, so I'm going to have just uv, right? 2 times 2 is 4. And then here I have 1/4 v squared minus 1/4 v squared. So all of this just simplifies to uv. So that's my function in terms of u and v. Now to put it all together, I need to integrate my bounds from 0 to 2, integral from 0 to 2, uv multiplied by the determinant of the Jacobian, 1/6, du dv. So this is separable, so this is the same as integral 0 to 2 u du, integral 0 to 2 v dv. So this is going to be the same, so I just need to evaluate it once. Integral from 0 to 2, That's going to be, let's see, u squared over 2. We plug in 2, we get 2. Times 2 times 2. That's going to be 2/3. Okay, yeah, so this one, there's a lot more work up front, but in the end, the integral that we have to actually set up is a lot simpler.
Mic off. Mic on.
So, yeah, you could have tried integrating this. That doesn't look fun at all. But then recognizing that we can just take each of these lines and just set it equal to whatever we want. Right, we can set this equal to v and set this equal to u, and then these edges, right, become like constant lines, and it makes things, quite simple. Yeah, I didn't realize that was the same as the example in the book. I just thought of it a different way when I first saw it. Okay, any questions from that one? Yeah, so yeah, I guess, let's see who asked me about it last night. So if you saw my comments on the homework channel, I guess that would kind of made you do more work than you're supposed to, but okay, so no questions from that. Which one next? Or did you all get all the questions no problem? Let's do this. Oh, that's cool. Wait, can I go higher? No, I think it only goes up to 10. Okay, which questions do you guys want to see next? Or do you want to move on to surface integrals and parametric surfaces? Okay, I'm seeing for number 9. Okay, you guys can keep voting on which ones you want to see. Number 9. Really? Okay. Okay, so number 9 said determine if this is if it's a gradient. If it's a gradient, calculate the indicated integral. Okay, so how do we check if it's a gradient? Well, we do we do the derivative of the y component, right? This is the y component with respect to x, and check if that's equal to the derivative of the x component with respect to y. Let me just say another way of writing this is to say that if I subtract the 2, I get 0. So this is the way that it's usually written. Okay. So I do the derivative of the y component with respect to x, and what do I get? I get 2. I do the derivative of the x component with respect to y, and I also get 2. I subtract them, I get 0. So that means that, yes, H is a conservative vector field, and I can write it as the gradient of some potential function. So H equals the gradient of something. Okay, I need to figure out what that something is. Okay, so what do I know? I know that if this is the gradient of something, that means that sine x plus 2y equals what? Equals the derivative with respect to x. So if I integrate both sides with respect to x, indefinite integral, and treat y as a constant, then what do I get? Integral of sine is negative cosine plus 2yx plus stuff involving only y, right? Because remember, y is a constant, plus a constant. Equals negative. Okay, so now I do the same thing for the y component. So the y component, cosine y plus 2x equals df dy. I integrate both sides with respect to y and treat x as a constant. Oops, with respect to y. And so what I get, integral of cosine is sine of y plus 2xy plus stuff involving only x plus a constant. Okay, so I know these two things have to be the same, right? They're the same function. Okay, so I'm going to look for terms involving that are in both of them, right? So what are the common terms? So that's going to be this one and this one. So f of xy equals 2xy, right? I only put it once. I don't need to put it twice because it only appears here once. Then I do all the stuff involving only x, right? What is this? I look over here. All the stuff involving only x, that's going to be just the cosine term. Minus cosine of x plus sine of y, right? That's my stuff involving only y, right? That's this right here, plus a constant. So that's my potential function. Now it asks me to evaluate this integral around here. So what does this look like? Um, well, actually, you know what? Let me just do this. So if I want to integrate h dot dr from 0 to 2 pi, right? That's the same as integrating the from 0 to 2 pi, the gradient of f dot dr. And the fundamental theorem of line integrals tells us this is just f of 2 pi minus f of 0. Okay, but actually, so we could do this, and this is fine, and we plug this in, we're gonna get 0. But here's the thing. What is this shape? This shape is just an ellipse, right? So t equals 0 and t equals 2 pi, technically those correspond to the same point on the ellipse. So really we're just integrating from one point to the same point again, right? This is the same as integrating from 0 to 0. So I don't even need to plug this in. I should know right away that since I'm going around an entire closed loop, right? Since I'm integrating around an entire closed loop, I can write it like this, right? I'm going around a loop. And I have a gradient here, so that means that this is going to be 0. Okay, so I don't need to actually evaluate any integrals. I know right away that since it is a conservative vector field and I'm integrating it around in a closed loop, I'm going to get 0. Okay. Um, let's see. I see 2 votes, or a vote for number 8 and a vote for number 7. Okay. Um, okay. So a path moves along. An object moves along this path. One of the forces acting on the object is this: find the work done by F. Okay, so remember, work is equal to force times distance. So if we do a small amount of work, let's see, actually, let me do it this way. It's F dot dr. And we're integrating from 0 to 1. So this is actually just very straightforward. This is just a line integral from 0 to 1 of 3x squared y x cubed. I need to put this in terms of t in a little bit. Dot r prime. R prime is 2, 2 times 1 minus t, negative. Dt. Okay, so like I said, I need to put this in terms of t and do that dot product. So I get from 0 to 1. And here, x squared, that's going to be 4t squared. So I have 12t squared times 1 minus t squared. Okay, so that's my first component. Second component is x cubed, so that's just going to be 8t cubed dot 2 minus 2, 1 minus t dt. I do the dot product, and what do I get? I have 24, and I'm going to, yeah, I'll just leave it. T squared 1 minus t squared minus 16 t cubed times 1 minus t dt. Integrate from 0 to 1. Okay, I'm going to go ahead and distribute everything out. So I have 24 times t squared minus, what is that? T cubed minus 2t cubed. Yeah. Plus t to the 4 minus 16 t cubed plus 16 t to the 4. And simplifying, I get 24 t squared. So that's minus 48 t squared minus 16 is what? It's minus 64. Here we have 24 plus 16, that's plus 40. Now we're integrating from 0 to 1. And finally, we get, it's going to be 8 t cubed, so t just goes from 0 to 1, so that's just going to be 8, minus, that's 16, and then plus 8. Right, so that's 24 over 3, 64 over 4, and 40 over 5, which is 0. Okay, so one thing to point out though real quick, this first one, this was 0 because we were integrating around a closed loop and we had a conservative vector field. This one is not a conservative vector field, and we're not integrating around a closed loop. It just happens to be 0, which is interesting. Okay, so I'll just comment for a little bit on 7. If you want to see a full discussion on how to do 7, you can scroll up in the chat, and there's a work through it a lot. But for number 7, it gave us some vector field, and it said integrate this around this loop where this was 2 and this was y equals 3. Okay, so we want it in a counterclockwise direction. So we want to integrate around here. Now, so you technically could have done Green's theorem, but the way the question was phrased, I'm pretty sure it just wanted you to evaluate the line integral. So we're going to do it that way. So we want to integrate h dot dr over c. Okay, so c is this whole loop. So what I'm going to do is I'm going to break this up. This is going to be integral from of c1. This part right here is going to be c1. That's from here to here. h dot dr plus integral over c2. Right, just like we would break up a regular integral into bits. c4 h dot dr. Okay, so now I just need to worry about each of these curves. So the weird thing about this question is that it doesn't give you the parameterization, right? We don't know what is r. Okay, and this is why I'm breaking this up, because to parameterize this whole thing is a little bit complicated, but I can parameterize each segment individually quite simply. Okay, so let's just look at C1. For C1, my y, I'll call it R1 of t, my y is constant. That's just always going to be 0. And what about t? Well, t I can just, or sorry, what about x? X I could say, well, that's just the same as t if t goes from 0 to 2. Right? Why not? It describes the same curve. It describes all of the same points. Okay, so then let's see, what was the h? H was
Mic off. Mic on.
okay. So where'd my pen go? There we go. So this was h. So if I want to put that in terms of r, so I have h of r1 of t. That's going to be, so y is 0, so that's 0. We have minus t, and that's 0, so there should be a j there. So that's 3t. Okay, r prime of 1, that's going to be 1, 0. So the integral from 0 to 2, y0 to 2, because those were the bounds on t, h dot dr is equal to the integral from 0 to 2 h dot r prime, so that's just minus t dt, equals, we integrate that, and we get minus 2. Okay, so now we do the same thing for the next one. I'm not going to do the integral, but I'll show you what the parameterization was. Oops. So the parameterization for the next one, r2 of t, that was, so now my x is fixed constant, and we'll do the same thing for t, for y. So y is equal to t, and t goes from 0 less than or equal to 3, and I do exactly the same thing. Okay, and that's going to give me this one right here, right? The integral along the second portion. Now when I do the third one, right, I can do the same thing. R3 of t. I have a couple options here. So the first thing that I need to be careful of is that this goes from 2 to 0, and that direction is important. Okay, so I need to know that as t increases, or whatever my bounds are, I start here and I end up here. So I know that y is fixed at 3. So one way I could do this is I could go, this is t, just like we did before, but now t goes from 2. I'm going to put it like this, but I know it doesn't make a lot of sense. But this just means that we're starting at 2 and we're going to 0. Right? So if I write this integral, it's going to be 2 down in the bottom and 0 up in the top. And that's going to make sure that I'm getting the right orientation. Or I could do this more manually, and I could say something like r3 of t equals negative t3. And now, so when we have negative, right, remember I want to start at 2, so I can start at negative 2. And then I need to end up at 0. So t goes from there to 0. So that works too. And there's a whole number of ways you can do this. That's fine. Really doesn't matter as long as it's describing from 2 to 0 along this line. And then here, again, same thing. You can do something like either of these. You could do
Mic off. Mic on.
you could do R4. That's going to be 0 t, with t going from 3 to 0. All right, and that works fine. And actually what you would find out here, since x is 0, if we convert h into terms of t, right, this whole thing is going to be 0. So this last integral is just going to be 0. There's no component there. Let's see. Well, for C4, it depends on how I parameterize it. If I went R4 of t equals 0 minus t, then yes, if I did minus t, I would have to go from minus 3 to 0. Just to make sure that when I plug in minus 3, right, I get 3, and then when I plug in 0, I get 0. Okay, or like I said, you could just use the regular curve and then just flip the bounds of where you start. So instead of going from 0 to 2 or 0 to 3, we go from 3 to 0, and that'll take care of the negatives for us. Okay, next, I guess we can go ahead and move on to parametric surfaces. Is everybody okay with that? Okay. So we've talked about parametric lines, right? So that's where we have something like r of t equals x of t, y of t, and z of t. Okay, so in a parametric line, right, there's really only just one variable, right? It's just t, right? So even though we have like, three-dimensional space or something like that, really there's just one variable. It's just in terms of t. So the goal now is we're going to do the same thing with, or actually, let me put it this way. We want to do the same thing with surfaces. So here, right, we can think of this, if we had our function in terms of x and y, great. But now, when we put it in terms of t, we've kind of eliminated a variable. Okay, so we have this long curve, whatever this is, and t, let's just say it starts at 0 and goes to 1. And this is t equals 0. Right, so I can think of t as being kind of this line segment, right? T equals 0 and t equals 1. And when we do this parameterization, it kind of takes this t and like stretches it and twists it and curves it and does whatever, and forms it into this other line that we were parameterizing. Okay, so we kind of just took a line, bent it up in whatever way we wanted, and that was our line. Okay, now we want to do the same thing, but with a surface. Okay, so the way this works is we're going to have some domain like this, and then we're going to do the same thing. We're going to bend it, we're going to twist it, we're going to form it into whatever shape we actually want. Okay, and this is going to kind of have the effect of eliminating a variable for us. Okay, let me find my examples. Let's see. One second. Okay, X, Y. Let's see. Okay, so I want to parameterize the part of the elliptic paraboloid blah 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 that lies in front of the x0 plane, the plane x equals 0. Okay, so if we want to do this, the first thing to know is if I can solve for one of the variables easily, that makes my whole life simpler. Okay, so here notice I can solve for x right away. Right, so I can say x equals 4 minus y squared minus 2z squared. Actually, you know what? Hold on. Let me back up. Let me back up a second. Okay, so this describes some surface. This describes a surface. What I'm looking for is I'm looking for a function r of u and v that gives my x coordinates in terms of u and v, my y coordinates in terms of u and v, and my z coordinates in terms of u and v. Okay, so now it's kind of weird. We're going from like a surface, like a scalar surface, to a vector function. Okay, so that means that every point along this curve is, so this is just a point, this is a coordinates x, y, z, but it's actually being described by a vector. Okay, so we're going to have vectors that point to every single point on this surface. And it's going to be described in terms of u and v. Okay, so if I can solve for one of the variables quickly, then I'm basically done, right? Because now I just set uh, y is equal to u, z is equal to v, and then I already have x in terms of u and v, right? Because I have it in terms of y and z. So I have x equals 4 minus u squared minus 2z squared. Right, so my function is going to be r of u, v. This is going to be 4 minus u squared minus 2v squared. That should be v over here. Times I plus uj plus vk. And this is going to describe my surface. Now, I have one more step. I need to describe what are the bounds for u and v. So just like when we have a line and we say it goes from t0 to t1, I need to say what is the domain for u and v for this surface. Okay, so let's think about what does this surface look like. So here I have x equals 4 minus this thing. I'll put minus this. So if I look at this from the side, it's going to look like this, right? And remember, we want when x is positive. So we only want the top half of this. So we only want the top half. So we're looking for the u's that give us y values in this range. Right, so if this is x, this is y. So I could have, and then actually if I'm looking at the top, it's going to look like an ellipse. So if I'm looking straight down at this domain, right? So now I have, here's my y and z. It's going to look like this. So it's going to look kind of like a bowl, and this is the edge of the bowl. So y, we can say that for y, it goes from, actually let's just solve this. This is y squared plus 2z squared equals 4. So I could say y equals plus or minus 4 minus z squared. So this up here is the curve root 4 minus z squared. And down here I have the negative of that. Negative root 4 minus z squared. Right, so those are my bounds for y. So I know that y is between these. And actually, why am I doing this in terms of y? I should have, this should all be in terms of u and v. So this is v, this is u, this is v, this is v, this is v, and this is u. So I have the bounds u is less than or equal to square root of 4 minus v squared and bigger than negative 4 minus v squared, and v goes from here, sorry, yeah, wait, and we're going from here to here. Did I get this backwards? So I might have written this backwards. This is from, let's see, when is v0? When u equals 2. Minus 2. That doesn't quite seem right. Why does this seem wrong? Okay, I'm gonna leave it like that. I think this is correct. Does anyone have any comments? Wait, am I over time? Yeah, I'm over time. Sorry, guys. Did not realize I took that long.